A lot of these are probably pretty common sense, like surface area, increasing temperature, stuff like that. But let's just go ahead and have a look at 5 rate influencing factors. Other than decompositions, particles have to come into contact in the right position and with enough energy for activation. That is what I emphasized in section 1 about having a successful reaction relies on having successful collisions that result in the valence electrons interacting with each other. Now, the rate of reaction depends on the collision frequency and on collision effectiveness. So the general idea is that if you can increase the number of collisions, you will then statistically improve the number of successful collisions, meaning in the right position with enough energy. So the 5 factors that I'm going to discuss that influence the rate of a chemical reaction. Number 1 is just the nature of the reactants. There's some substances that are just more reactive than others. For example, pure potassium in water by itself is more reactive than, let's say, a cube of sugar. Okay. Number 2 is surface area. Sorry, just like letting people in here. Number 2, surface area. Increasing the surface area is going to increase the amount of interactions between molecules and therefore increase statistically the number of successful collisions. 3, which should be the most obvious one, is temperature. By increasing temperature, you increase the kinetic energy, which means molecules or atoms are moving around faster, which means they're going to interact more. Number 4 is concentration. Again, if you increase the amount of reactants, then you're going to increase the number of molecules that have the potential to interact. And finally, number 5 is the presence of catalysts. I'll go through each one separately. Number 1, the nature of the reactants. Now, different substances are going to have different abilities to react. For example, hydrogen combines strongly with chlorine under certain conditions, but under the same conditions, it hardly reacts at all with nitrogen. So this is a reaction between hydrogen. So that greenish color you're seeing, the yellowish green, is chlorine gas.
Okay, go for it, Pete.
So they mixed the hydrogen and the chlorine gas inside the bag, and the flame that you saw there, that was what provided the activation energy. I think I've mentioned it before. With activation energy, you can mix hydrogen gas and chlorine gas. It doesn't mean they're going to react just by physically being in contact with each other. You need that activation energy to get the reaction going. Once you overcome activation energy, especially for exothermic reactions, generally the energy that's produced from the reaction is enough to keep the reaction going, if you understand what I mean. Another example is sodium and oxygen combine more rapidly
sodium in a spoon.
than iron and oxygen.
Plunge it into a jar of oxygen. It burns to form the very stable compound sodium oxide.
This would also be a good example of concentration. So when you see it originally burning, this is just regular air, which is only 20% oxygen. But when they move it into the cylinder, they've covered it because there's 100% oxygen in here. And so you can see the difference with how much it burns in pure oxygen versus the air. So that's the nature of the reactants. It's just some substances are more reactive than others. Number 2 is surface area. Gaseous mixtures and dissolved particles can mix and collide freely. So reactions with them happen more often and faster. I think it was last week when I was talking about intermediates and things, I mentioned homogeneous reaction with hydrogen gas and iodine gas. Homogeneous reactions are when you have different phases involved, like between a gas and a liquid, or aqueous and solid, something like that. Heterogeneous, sorry, I got that completely switched around. Homogeneous reactions are when, because I started reading the definition and then I got sidetracked. Homogeneous reactions are when everything is in the same phase. So the example I had last week or the week before, can't remember anymore, hydrogen gas plus iodine gas yields hydrogen iodide. So you have H2 gas plus I2 gas yields 2HI gas. This is an example of a homogeneous reaction because everything is gas. But you can also have heterogeneous reactions where the reactants are in different phases. Now, for a heterogeneous reaction, it can only occur when these two phases are in contact. So the surface area, especially for solids, is really important in determining the rate of reaction. Why it's important for solids more than anything else is because the atoms in a solid cannot move, not like in a liquid, a gas, or a solution where the molecules have the freedom of movement. So the more surface area for a solid, the height of the rate of reaction. You probably can apply real life scenario if you think of dissolving cubes of sugar in a glass of water versus granulated sugar in a glass of water, or like a chunk of salt versus salt granules. If you have the powdered sugar or the granulated sugar that's not in cube form, that's going to dissolve much quicker. I think I talked about that a couple of chapters ago, many chapters ago, when we talked about solutions and how they're made, because dissolving occurs at the surface of the solid as the atoms dissolve or the molecules dissolve. One example is zinc and hydrochloric acid. They're going to react in a single replacement reaction. Do I have the equation? Yeah, I do, so I don't need that. So solid zinc is going to react with hydrochloric acid. The zinc is more active than the hydrogen, so it's going to replace. If you remember all the way back to chapter 8, which I'm just starting with grade 10 now, this is an example of a single replacement reaction. And we had the activity series of metals. But as I told you guys last year, you generally don't have to memorize that list if you understand the periodic table and what it means. So as I was discussing with grade 10 this morning, if you want to compare, you've got, well, let's do the groups 1 and 2. The group 1 and 2 metals are going to be the most reactive. Group 1 is the most reactive because they have an S1 configuration. And that means that they just need to get rid of that one electron to be like the noble gases over here. So they're super desperate to get rid of it. Group 2 is going to be the second most reactive metals because they have an S2 configuration. So they're going to be a little bit less reactive than group 1 because they do have 2 electrons to get rid of instead of 1, but they're still going to be more reactive. When you get to the transition metals, these metals up here are going to be more reactive than these metals down here. And if you can't remember, just look at where the precious metals are. You have silver, gold, and platinum, which are really close together. Right down here, you've got silver, you have gold, and then platinum is right next to gold. So these are the precious metals because they're quite unreactive. So you just go kind of the opposite direction and you see where the active metals are. Anyway, just a quick review of that. So in the activity series, the only thing that I recommend is understanding where hydrogen is in that list, and hydrogen is pretty close to the bottom. I think copper, definitely the precious metals, maybe mercury is underneath hydrogen. So most of the other metals, when you're dealing with chemical equations, most of the metals will replace hydrogen. Anyway, so zinc replaces the hydrogen in the reaction, forms zinc chloride and hydrogen gas. Okay. All right, so this reaction, of course, is going to occur on the surface of zinc, because if you have, let's say that's my hydrochloric acid solution, and here is my chunk of zinc. The reaction, remember I said a couple of slides ago, the reaction occurs only where the two phases come into contact. That's going to be at the surface here. So the reaction is only going to occur on the surface there. Oops, okay. So a piece of zinc measuring 1 centimeter on each edge is going to have 6 centimeters of contact area, compared to if you have a powdered form, it can be up to 1,000 times the surface area.
Okay, this is the experiment. Here we've got 3 beakers, each containing dilute hydrochloric acid, and these containers have got marble in them. The chemical name for marble is calcium carbonate. Here the marble is divided up into fine powder. In this one it's relatively, well, medium-sized chips, and here there's fairly large chips of calcium carbonate. Now what we're going to do is going to put them into the dilute hydrochloric acid, and just by observing it make a note of the rate of reaction, how fast the reaction goes. In other words, how fizzy it gets. This is the one with the large chips. As you can see, the reaction's fizzing. It's not particularly rapid, but it's going fine. And the reaction shouldn't take too long to complete. With the medium-sized chips, however, you can see the reaction's much faster.
Now you can see that the reaction is more vigorous because you actually see bubbles on the surface of the liquid. Instead here, the bubbles were quite a bit smaller. And you didn't have any bubbles on the surface.
And then we come to the powdered calcium carbonate.
That should be pretty obvious.
It's fairly obvious to see that the surface area, increasing the surface area, increases the rate of reaction.
Okay, so that is surface area. This has real life consequences when you talk about things like coal mining. A lot of times you might hear in the news about an explosion in a coal mine. And this is because when you dig for coal in a mine, obviously you're going to have a high concentration of coal dust in the air inside the mine, which is underground. And if there's any kind of spark at all, that can cause a huge explosion throughout the mine. But if we use lumps of coal like we do on a barbecue, we know that big chunks of charcoal burn quite slowly. But the rate of burning is going to increase if you break up that coal into smaller pieces. So sometimes, depending on what you want to cook and how fast you want to cook it or what kind of food you're cooking, you could use fairly large charcoal bricks, or you can use charcoal chips. I know that you can buy them in different forms here, depending on how long you want the barbecue to to run. Sometimes you want to cook the meat or the food slowly over low heat for a long period of time. Sometimes you really want like a flame, like a really high flame to get that nice charcoal flavor. So you can adjust the size of your chips based on that. So if you've ever gone barbecuing or gone to a barbecue, then you can apply your knowledge of chemistry to adjusting how you cook the food. So here I've got, I should actually change that because it's not the Ukraine. It's just, let me change this real quick. Since Ukraine is in the news right now because Russia's about to invade, it's not the Ukraine, it's just Ukraine. So this is a coal mine explosion in Ukraine. So obviously it's on fire and there's the explosion. Just had to let my dog in. Okay, so that's an example of the effect of surface area. Number 3, hopefully the most easy to understand factor that affects reaction rate is temperature. Increasing temperature increases kinetic energy, which can result in a greater number of effective collisions. If the number of effective collisions increase, then the reaction rate will increase. To be effective, the energy of the collisions must be equal to or greater than the activation energy. At higher temperatures, more particles have enough energy to form the activated complex when the collisions occur. So the rise in temperature produces an increase in collision energy as well as in collision frequency. So not only are the molecules moving around faster, which means they can interact more and possibly hit each other more, but they also have higher speeds. So they're hitting each other with a higher energy. So the two criteria that are required for effective collisions, that is position and energy, are fulfilled by increasing temperature. Decreasing temperature obviously has the opposite effect. The average kinetic energy decreases. So that means they're moving more slowly, which means they collide less frequently and with less energy. So this produces fewer effective collisions. Beginning near room temperature, the reaction rates of many common reactions roughly double with each rise in temperature of 10 Kelvin. It's actually quite a big increase if you're raising the reaction rate doubly with every 10 degrees Kelvin. Next is concentration. So in this picture on the right, in picture B, the piece of coal is burning in regular air, and in picture A, it's burning in pure oxygen, very similar to the video you saw before with the sodium. Because air has 20% oxygen, pure oxygen, obviously 5 times the concentration. So substances that react with oxygen in the air will react even more strongly with pure oxygen. Unfortunately, we are not on site, so I can't show you this, but a few years ago, I demonstrated this by mixing potassium permanganate and hydrogen peroxide, because one of the products is oxygen gas, and then you basically, I didn't have any of the flints, like the long matches, but I did just basically light a piece of paper on fire, and then when you put it into the flask from the reaction of the potassium permanganate and the hydrogen peroxide, the flame gets a lot brighter, which you'll see here. They're doing the same reaction. So you see the bubbles that are being produced at the bottom of the flask. That's oxygen. And so when you put that in, you're exposing it to 5 times the amount of oxygen, so the fire burns brighter because the reaction rate is increasing. So that's concentration. Okay, blah, blah, blah. What's this one? I think he's going to do that experiment I talked about. Yep. Hydrogen peroxide, potassium permanganate. Yep, there it is. Potassium permanganate. Two pretty commonly found items in a lab. Potassium permanganate's that really, really dark purple crystal. If, by the way, if you get potassium permanganate on your skin, it stains it yellow for some reason. I don't know why that is. So that's basically what I did in the lab a few years ago. Anyway, okay, in homogeneous reaction systems, the reaction rates depend on the concentration of reactants. If the number of effective collisions increases, of course, the rate will increase as well. In general, there is an increase in rate that is expected if the concentration of one or more reactants is increased. I really like this graphic because it really shows you how increasing the concentration increases the number of possible collisions, therefore probably effective collisions. So in the first one, we have only one item of each reactant, so there's only one collision possible. If there's two of each, you increase that to 1, 2, 3, 4. If you increase the red one by 1, you increase it to 1, 2, 3, 4, 5, 6. And then finally 4 of each. I'm not even going to bother counting all that, but it's a lot. So with only 2 molecules, there is only one possible collision. When there are 4 molecules, you multiply that times 4. Under constant conditions, as the number of molecules in a system increases, so does the total number of possible collisions. This should make sense to you, like logically in your brain. If you add more molecules, you have more collisions. And always, if you have more collisions, you increase the probability that you will have a successful collision, therefore increasing reaction rate. The last one is the presence of catalysts. Now, the reason why catalysts are going to increase reaction rate is because they lower activation energy, which is the assignment that you just worked on yesterday. So here we've got a diagram with the top one with an activation energy of 75, that is uncatalyzed. And then we have a chemical catalyst. In this example, they use the iodide ion, and that reduced the activation energy to 58. And when you catalyze it with an enzyme, it drops it all the way down to 4. So the reason why this increases reaction rate is that it just makes it easier for the reaction to occur by requiring less energy to activate it. I go back again to the analogy of rolling a ball up a hill. If you can lower that hill, it takes you less energy to get over it. And that's the purpose of a catalyst. The nice thing about a catalyst is that it reduces activation energy without taking part in the reaction and without being used. Some reactions just by nature are slow, so we can use a catalyst, which is a substance that changes the rate of a chemical reaction without itself being permanently used. The action of a catalyst is called catalysis. A catalyst provides an alternative energy pathway or reaction mechanism. Reaction mechanism was that thing that I talked about in the very beginning. So let's say if uncatalyzed, your reaction mechanism includes 4 steps, but with a catalyst, it goes down to 2 steps. That obviously would take less time. So the potential energy barrier between reactants and products is lowered. The reaction rate of the decomposition of hydrogen peroxide can be increased using a catalyst. Here, they use a catalyst called manganese dioxide. which is a black solid. This is a chemical catalyst. Okay. Catalysts do not take part in the reaction, so they do not appear among the final products. Some catalysts may participate in one step along a reaction pathway and be regenerated in a later step. So they might be temporarily used, especially if you're talking about a chemical catalyst. It might provide that shortcut through the reaction mechanism and be an intermediate, but it gets regenerated, so it's not permanently used. Now we can divide catalysts as homogeneous or heterogeneous, depending on if they're in the same phase as the reactants in the system. Obviously, a homogeneous catalyst is the same phase. Heterogeneous is a different phase. Okay. I don't want to talk about rate laws yet.